In our previous video, we saw how we can verify the impedance of a coaxial line through Microstrip Office. However, it is not easy to fabricate a coaxial line, and in fact, usually you just buy them ready-made. However, for microstrip lines, the situation is quite different. It is quite easy to fabricate it, and in fact, it is commonly done, and its versatility is what makes it particularly useful. So to actually design a line, we can use the equations that are given in the notes, and those would work to some extent, and they're quite approximate as is specified in the notes. But we can also use a very useful tool in Microstrip Office called TX-Line. To get it, we just need to click on Tools and then TX-Line. Now, in this window, as you can see, you have a number of different types of lines that you could work on. There is microstrip, there is a strip line where you've got a ground plane above and below the line. There is a coplanar waveguide. There are a number of different topologies that you can use for a printed circuit transmission line. However, we've only looked at microstrip lines, and we will just be looking at that in this tutorial. However, be aware that if you need any other type of line for your specific design, it is possible to design those also with TX-Line. So let's go back to the Microstrip tab. You can see that there are quite a few boxes that we need to fill in. Now, you can either choose the dielectric material from a pull-down menu, and if you do so, for example, if we select RT Duroid, then the TX-Line calculator will automatically give you the dielectric constant and other parameters like the loss tangent, for instance. In our case, we are going to design our transmission line on FR4. FR4 is a very cheap substrate which is very widely used commercially, and so I think it is quite useful to use that substrate for our design. When you're inserting your own data, it doesn't matter what the dielectric is set to appear, because you can just overwrite every box that you need to change. So let's go into the dielectric constant first, and for FR4 this is 4.7. The loss tangent, which quantifies how lossy the dielectric is actually usually a bit bigger than 0.001. In fact, I think is 0.05 most of the time. But we'll leave it alone for now, and then we'll come back to it in a minute. The impedance of the line that we want to design would be 50 ohms. The frequency at which we're working would be 1 gigahertz. The electrical length of the line would matter if you wanted, for example, to design a quarter wave transformer, or if you wanted to match a line by using a specific length of line. But in our case, it doesn't matter. If you have a 50 ohm line, then it doesn't matter what length it is, it'll always be 50 ohms as a characteristic impedance. Then we need to select the height of the substrate, which is already correct, is 1.6 in our case, millimeters, and then the thickness of the metal on top of the substrate. This doesn't really matter. We'll leave it alone for now and then see how this influences the line. As we said in the notes, the characteristic impedance of the line is largely due to the width of the signal line and the height of the substrate. So we're just going to click on the right pointing arrow and see what we got. We got 2.91 millimeters for our line. Now let's see what happens if we choose a different loss tangent, for instance 0.05. You can see that the width of the line hasn't changed by a great deal. Also, if we change the thickness of the metal and say we choose 10 micrometers, again there's been a minimal change in the line width. So we'll just leave this to 1 for now. We can leave the loss tangent on 0.05. It doesn't matter a great deal. So the width of our line is 2.9 millimeters, really. Now, how do we test it? We cannot extract a line directly from TX-Line into the simulator. We just have to remember our parameters, and then we'll insert it into a specific model which is used for microstrip lines. So let's go to circuit schematic, open a new one, Microstrip on FR4, use the Ctrl L to fetch an element called mlin, which stands for microstrip line, and place it in the schematic like so. Then we need another element to specify the characteristic of the substrate that we're using, and that element is called msub. So again, Control L, type in msub, and you get a substrate definition. Double click, place on the schematic. So the first thing we need to do is to change the various parameters of our substrate to match the one that we've used for our design. First of all, the electric constant ER, we need to set that to 4.7, both in the ER and ER nominal box. The height of the substrate is 1.6 millimeters. The thickness of the metal, as we've seen, doesn't matter a great deal. However, we used 1 micrometer, which is 0.001 millimeters, so we'll use just that. Rho is the bulk resistivity of the metal compared to gold. We'll leave it to 1. It won't matter a great deal. The loss tangent can be 0. As we've seen, this parameter also does not alter the characteristic impedance of the line by a great deal. So we've got pretty much all the parameters that we needed. Now, we are going to have to set the width of the line to whatever TX line calculated, which was 2.9. And in terms of the length of the line, we have to set it to 1/8 of the wavelength to actually verify the characteristic impedance, just in the same way as we did for a coaxial cable. First of all, let's put our test port on the schematic, terminate the line with a short circuit, and then calculate a length for the line equal to 1/8 of the wavelength. So in the case of a microstrip line, the situation is a little bit different, because we can't just use the dielectric constant alone to calculate the speed of propagation of the signal along the line. As we've seen in the notes, part of the signal will be traveling in air and part of the signal will be traveling in the dielectric. So we need to get a kind of average or weighted average dielectric constant to account for this phenomenon. And that's the effective dielectric constant epsilon E. And this can be calculated with the formula that is shown. So if we calculate it in our case using 4.7 as a dielectric constant and using 1.6 as a height and 2.9 as a width, we get 3.52. This translates in a velocity of propagation along the line equals to 0.533 times the speed of light. So it's almost half the speed of light. And then, of course, we need to calculate 1/8 of the wavelength. This is obviously just 1/8 of V over F. The frequency at which we will be simulating is 1 gigahertz. We can choose other frequencies, but we'll use this for simplicity. So the actual velocity of propagation numerically turns out to be 1.588 times 10 to the 8 meters per second, and the wavelength divided by 8 is equal to 19.9 millimeters. So we can go back to our schematic, and we change the length to just that, 19.9 millimeters. Now, what we need to do is go to Project Options and set the right frequency of simulation, in our case 1 gigahertz. Then we can go to Graphs, add a new graph, a rectangular graph, we'll call it Microstrip Z-Note. We right click on the graph, add a new measurement. It'll be an impedance measurement at port 1 from Microstrip on FR4, and we'll just look at the magnitude of the impedance. Then click Apply and OK. And then if we simulate, we get almost exactly 50 ohm as a characteristic impedance of the line. If I change the scale of the graph, you can see how close it is to 50 ohms.